When we look at a highly accurate simulation of a rotating black hole, we see something quite different from standard science fiction. This level of detail requires general relativistic ray tracing, or GRRT. By mathematically integrating the paths of light rays, null geodesics, through curved spacetime, we can map exactly how this immense mass distorts its surrounding environment. Notice that the accretion disk is vividly blue. While many popular diagrams use false color orange to map luminosity, matter moving at relativistic speeds toward the observer experiences severe Doppler boosting, shifting its visible light spectrum strictly into the blue. The black void at the center is bounded by the event horizon. This is the exact radius where the escape velocity, necessary to break free of the black hole's gravitational pull, equals the speed of light. GRRT gives us a perfect geometric description of the spacetime outside that boundary. But to understand what happens to the geometry inside the event horizon, we have to discard several classical assumptions about gravity. The simplest black hole model, the Schwarzschild metric, describes an idealized object with no spin and no charge. Cross its single horizon, and you unavoidably hit a central point where physics breaks down. But in reality, astrophysically realistic black holes possess massive angular momentum, which fundamentally alters their entire internal structure. Outward centrifugal forces slow the inflow of space, creating a second, deeper boundary inside the event horizon. This is the Cauchy horizon. If you only use classical general relativity, the math indicates this inner horizon is perfectly stable. It acts as a gateway, theoretically allowing an observer to pass through into other regions of spacetime. But that mathematical promise falls apart when we account for quantum mechanics. When the quantum vacuum interacts with the specific geometry of the Cauchy horizon, the gravitational forces generate an effective Hawking temperature that drops below absolute zero. A negative temperature in this context is not a rounding error. It dictates a catastrophic ultraviolet divergence in the radiation spectrum, generating a massive wall of infinite energy that physically destroys the inner horizon before anything can ever cross it. To see exactly how this destruction occurs, we can track the equations of geodesic deviation for an observer in radial freefall. At the outer horizon, gravity pulls stronger at the feet than the head, stretching the observer into spaghettification. Approaching the inner Cauchy horizon, physical forces invert. Outward stretching becomes intense spatial compression. The observer is severely flattened into pancakeification. This inversion from stretching to crushing is a purely classical phenomenon, dictated entirely by a specific variable in the spacetime metric, known as the delta double prime term. Classical physics tells us the spatial forces flip, but to determine if the observer survives the trip, we have to look at how the quantum vacuum itself reacts to this intense compression. This requires a shift from tracking the paths of classical particles to the framework of quantum field theory. The common heuristic for Hawking radiation pictures virtual particle pairs emerging from the vacuum and being ripped apart by stretching tidal forces at the horizon. That analogy completely breaks down here at the inner horizon. Particles aren't being ripped apart, they're being crushed together from all directions. Instead of discrete particles, we have to model continuous waves. We measure how wave modes originating in flat space, a Minkowski vacuum in the distant past, scatter and distort as they pass through the dynamically forming geometry of the black hole. Physicists use a mathematical tool called a Bogoliubov coefficient to calculate the expectation value of these excited modes as they emerge in a different vacuum state. By measuring the scattering of these continuous waves, we can calculate the exact spectrum and intensity of the Hawking radiation that a local infalling observer would perceive. This effective surface gravity equation dictates the temperature of Hawking radiation hitting the observer. Notice the numerator, the classical delta double prime term. Near the inner horizon, this term becomes negative, forcing the entire temperature equation to flip its sign. At the outer event horizon, this exact same equation produces a positive result, yielding standard thermodynamics. But as the observer descends even deeper, the localized crushing geometry of the inner horizon mathematically forces the temperature of empty space itself to drop below absolute zero. This chart maps the radiation's spectral intensity. At the outer horizon, the spectrum is a standard bell curve, tapering off at high frequencies. But at the inner Cauchy horizon, this drop-off becomes a massive upward spike, an ultraviolet divergence. This hard data proves that the negative temperature generates a wall of infinite quantum radiation, completely obliterating any classical model that suggests a peaceful crossing of the inner horizon. This Penrose diagram shows the black hole's causal structure, mapping wave behavior onto physical geometry. Tracing these null rays, the scattered quantum modes, we follow the energy flow. This radiation piles up infinitely at the inner horizon boundaries. This infinite influx of negative temperature radiation triggers a mechanism known as quantum back reaction in the S-wave approximation. Semi-classical physics tells us that this radiation carries an immense quantum stress energy contribution. It places infinite physical stress directly onto the fabric of space-time itself. The inner horizon cannot mathematically endure this stress. Even if a black hole is perfectly isolated, the mere existence of the quantum vacuum forces the underlying geometry to violently respond. Under this extreme quantum pressure, the inner horizon completely destabilizes and collapses into a chaotic, hard singular line. Driven outward by the negative temperature, the inner horizon morphs entirely into a non-traversable space-like singularity. This space-like singularity effectively truncates the Penrose diagram. It places a hard physical limit on the interior, permanently cutting off any access to hypothetical white holes or other universes. The classical promise of a traversable wormhole is merely a mathematical artifact. In reality, the roiling quantum vacuum ensures that at the inner horizon, space and time as we know it simply end.